Hello, everybody, and thank you for joining us here today. My name is Matthew Reid from Equipco. I'm a Hydronic Specialist with the company, and I'm going to be running your training today on Hydronic Fundamentals, Hydronics 101. So again, the company I work for is Equipco. We have branches in every province, coast to coast, all across Canada, and we're always happy to help whoever we possibly can. Today on the 101, we're going to be going through just your basic getting started, what you need to know about hydronics as a complete basics. And we're going to go into some fundamentals, some of the formulas to remember. We're going to spend a bit of time on water quality, actually quite a bit of time on water quality, speaking about what exactly you need to know about the water inside of a system and specifically what it does with regards to the warranty of a system. After that, we're going to be doing the why and where of using air, dirt, magnetic, and hydraulic separators, which are what's referred to as hydronic trim or trim packages. And then we're going to be going through proven piping systems in hydronic schematics. So as we get going here today, I just want you to know that you can feel free to reach out to Equipco at any time for any hydronic questions that you have. We're always happy to assist wherever we possibly can. 𝘕𝑒quipcoltd.com is the website that you can see all of our contacts and information as to who we are and find your local representative. So let's get started. With regards to hydronics, you're going to find yourself in two scenarios. Your first one is going to be a re-and-re. This is going to be an extremely common situation. You find yourself in the industry where you're going to be replacing an existing boiler or pieces of a hydronic system that's already existing. This means that you're not going to be doing a complete redesign. You're not going to be going from scratch. It's just basically changing out the equipment that is already there. That's referred to as a re-and-re, which means remove and replace. Usually fairly standard, but a couple things to consider, such as like the space you have, what was existing, was it working, stuff like that you're going to want to really dive into and make sure you get your re-and-re or remove and replace of a boiler done properly. The second scenario you're going to find is a whole new system. Whole new systems are going to be when you're talking about usually a design build package or a custom home, or maybe you're working with an engineer that's doing, track housing or custom homes where they want to use hydronic as the base sort of heat. Now, a new system is going to give you a lot more flexibility as to exactly what you want to do. And for new systems, just like re-and-res, the most important thing to make sure that you have identified is a clear view of success between what you can do, what the homeowner wants, and what the builder wants. As long as you have a clear vision of exactly how the system is going to work and operate and what they needed to do versus what you're going to install, your systems are going to go quite smoothly from start to finish. But it's all about front-end loading these packages to make sure that, again, I said it before, I say it again, a clear vision of success of what the homeowner wants, what you want, what the contractor wants, what the wholesaler wants. Everybody involved needs to be completely upfront about what exactly the package is going to look like and what it's going to do. So let's just back up a little bit. Re-and-re. What is a re-and-re? Again, I mentioned it's a remove and replace. Usually it's a new boiler adapting into a current or an existing system. The reason for this, sometimes folks are doing maybe the boiler's old, time for an upgrade, put something new in. Or maybe they're doing an existing upgrade to a home, such as a home renovation, putting on a new wing, or maybe they had the hydronics doing the kitchen and the bathroom and radiant before, and now they want to add some radiant to, a sunroom, or maybe add a bit of snow melt or something like that. That's going to be something that's classified as a re-and-re, where you're adapting to an existing system. So some common questions that you're going to want to ask, and this is going to be across all stages, is, I got a list right here. I'm going to start with the very first one, which is in my opinion, the most important. What is the budget that we're going to be looking for in this job? If you have a budget of, let's just say it's $5,000, that's going to be basically a new boiler, and that's about it. If they have a budget more like $10,000 to $20,000, now you're talking about doing an addition to a system, really going a bit further down the rabbit hole of, adding in some heat emitters such as radiators or snow melt and stuff like that. So the point with the budget is that if they come to you with all these needs but have a very small budget, that's not likely realistic inside of a hydronic system. The second question you want to ask for a re-and-re is the current system working as effectively as possible? Meaning essentially, Did the boiler ever work right in the first place? Did they have hot and cold spots in amongst the house? Was the heat effective? Was the cooling effective? Did it work as the homeowner intended it to and as they wanted it to? If it didn't, this is a good chance to dial in the finer details of a hydronic system, make sure we get it working right moving forward. Second, or next on the list, is it sized right to begin with? There's a couple cheat codes you can use with regards to sizing a boiler or sizing your heat emitters, but really what the code dictates is that a heat loss must be done in order to install one of these systems. And it's not just hydronics, this is forced air, this is across the board. A heat loss must be done in order to see if a system is going to be sized right. But a couple things that you can tell without doing a heat loss is you can usually talk to the homeowner. Did they have a lot of short cycling? Did they have a lot of failures? Did they go through igniters quickly? That's a good sign that the system is oversized. If the system had a hard time keeping up in the winter, if they ran out of hot water with an indirect water heater, that's a sign that the system is going to be undersized. So that's a question you're going to want to make sure that you have isolated and identified, because again, this is the time to get that sort of thing addressed moving forward. Last one here on the list is the current system designed appropriately to accommodate for a modern boiler or system upgrade. What I mean by this is that we have come leaps and bounds in the last 10 years, and from that we've come leaps and bounds from the last 40 years before that, where we have old systems with giant piping, gravity vents, or sorry, gravity circulated systems, where you have to do a little bit of work to change that old style into your new hydronic system. So if you're taking out a really old system, putting in a brand new, you're probably going to be looking at more than just a boiler replacement. Probably going to be the addition of some pumps and some trim and stuff like that. So that's a common question that we want to make sure that we get addressed before we do anything too deep in the re-and-re. Re-and-re should be very straightforward and simple. We're just removing the existing, replacing with something new, but it doesn't always work like that. So I want to talk about some of the common issues that we come across, and I kind of alluded to a few of these in the previous slide, but this is the stuff that needs to be addressed. Common issues that I see all the time, every single day, and this one I see quite literally every single day, is wrong pipe size. Wrong pipe size is almost always going to be the piping is going to be too small. For example, if you have a 100,000 BTU boiler and you try to pipe that boiler with half-inch pipe, I don't care if it's PEX or copper, I don't care, but just anything that small, there's no way you're going to carry 100,000 BTUs through pipe that size without moving it through that piping at the speed of light. So piping needs to be sized properly for the BTUs that you are moving. We get that one all the time. There's beautiful charts online. There's apps you can use to make sure you get the pipe sized right. That's a good place to check to make sure that you're not going to have that common issue come up. Another one that we come across is the wrong circulator size. We deal with circulators all day, every day. Hydronic systems are designed to have the right flow going at the right speed to the right emitter. Wrong size circulators can either give us underpumping or overpumping situations where we're sending too much heat to an area or not enough heat to an area. Wrong circulator sizes can be quite an issue with delivering the heat that is required. You can sometimes get around this by using balancing valves, but it's also just as easy to actually size your circulator properly and correctly and let the system do what it's designed to do, which is heat adequately based on the heat loss. Next one on our list, poor water quality. So I want you to sit there and I want you to think to yourself right now, if you've never seen a hydronic system, maybe you have, and again, I'm going to hope that you have on this one. I want you to think about what color the water should be in a hydronic system. The answer to that question, 99% of the time, should be clear. It should be crystal clear, perfectly clean water. If it's not clear, it should be colored. And by colored, I mean red or green or whatever other color glycol is coming in nowadays. Those are the two big colors that you're going to find. If it's anything other than that, it's going to mean usually that's either going to be black or brown. If you find your water is black or brown, you have poor water quality. You're going to have a tremendous amount of what's called total dissolved solids or particulates in the system, which is going to be impeding the heat transfer from your radiators or radiant inflow PEX tubes or copper pipes inside of your air handler. If you have dirt inside of that system, Poor water quality is going to lead to a premature failure of our heat exchangers, not enough heat transfer through our heat emitters, and water quality is going to be something that needs to be addressed before you put a new boiler into a system. Otherwise, the problems that you created yesterday are going to follow you to tomorrow, even with a brand new system. So addressing water quality is something that you want to make sure you get done and taken care of. Last one on our list is the wrong placement of various system components, such as the expansion tank. All I want to say about this one, because this is going to be a bit more of an in-depth conversation, is that a lot of the times we have pieces in a system that are required, but they're put in the wrong place, which causes us problems usually with flow or with dirt and debris inside of a system. So it all goes back to the three pieces that I just mentioned. If we have pieces in the system in the wrong place, that can lead to poor water quality. If we have pieces inside the system, again, that are in the wrong place, such as your expansion tank going where it shouldn't, that'll affect your circulator sizing, or it can cause a undersized circulator to perform very, very, very poorly, and it'll make you need to oversize your circulator, which can be very, very, very expensive. So in order to get it right, again, according to the CSA B214, according to the code, systems must be designed, meaning that someone has to own the design of a system. And we'll get back to that here in just a moment. But the whole point of kind of talking about these common issues is not to scare you away from it. In fact, we highly encourage you to give it a shot, but we want to make sure that you're protecting the equipment and protecting your work. When you change out a piece of a system, you own that piece now. You don't own the whole thing, but you own that piece. And if your mistakes in this area of isolating and addressing the system is done wrong, then that can lead to problems with your piece that you just installed, and then you're going to have to do all sorts of callbacks and work on the system. That's something that you could have avoided in the first place. So that leads us to new systems. This is a complete mechanical system. You got a brand new boiler, new trim, new heat emitters, indirect water heaters, stuff like this, where it's going to be the entire thing completely done and designed, completely done and installed by your contractors, maybe yourself. And these are the things that you're going to want to ask. Number one, again, what is the budget? If they come to you with $5,000 for a whole home heating system, that is not nearly anywhere close to where you should be for a system such as this. Hydronic systems versus air source systems or forced air are about 15 to 20% more expensive to go hydronic. Your life expectancy is going to be longer in a hydronic system, so that's why it costs a little bit much more up front. So come with the proper budget, get the best pieces of products that you can, long life of a system, everybody's going to be happy. A couple concerns that you want to make sure that you get out of the way: structural concerns, ceiling heights, mechanical room size and location, and complete system requirements. I'm going to talk about that last one here in a second. But ceiling height and mechanical room size and location are huge. A lot of the times, folks are not super geeky and nerdy and love hydronics like I do. I want to see my boiler in my living room. I want to put my TV behind it because all I want to look at is my boiler running all day, every day. That makes me super happy. But most of the time, folks don't want to see that. So where do they put the hydronic system? Under the stairs, in the basement, out of sight, out of mind, never look at it again. They give you the flooring space of about the size of a postage stamp and expect you to put a boiler, an indirect, manifolds, a radiant floor, snow melting, air handlers, all sorts of stuff down in there. You got to have that proper understanding that to get a good quality system, we're going to need a little bit of room. So make sure that they have a good understanding that we're going to need more than just, you know, a 4x4 room or a little closet under the stairs. We're going to need a little bit of room to get these systems in. They are a little bit, I'm not saying they're large and cumbersome. We can design them quite small, but just know that if you plan on putting in a 80-gallon indirect water heater, but your ceiling height's only 48 inches or something like that, that's not something that's going to work. Our last one I have listed here is the complete system requirements. Basically what I'm saying here is, I'll go back to the very beginning, a clear understanding of what you can do, what the contractor can do, what the wholesaler can do, what the builder wants, and what the homeowner wants. A clear vision of success for everyone is going to be key, making sure that we get it done right the first time. So here's some things to note. The new systems must be designed in accordance with the CSA B214 Hydronics Code. And here is some of the key takeaways that I like with regards to the Hydronics Code that you can use to make sure that you sell your projects properly. 4.1a, All system components shall be selected according to the system design. That means that someone owns the design for this system. If the contractor does it themselves, that's fine. If they get someone with a BCIN to do it, again, completely fine, and that's usually the better way because that carries some liability insurance, or maybe they're going to get a P-Eng to do the design. Doesn't matter who, but someone legally owns that design of that system and says, yes, this will work. Keep that one in mind. 4221, the heat source, meaning the boiler, shall, or in some cases an air-to-water heat pump or whatever. The heat source output shall not be less than the heat load indicated in the system design. A couple things to unpack here. Number one, bit of common sense. If you do a heat loss for the building or for the home and the heat loss is 50,000 BTUs and you put in a 30,000 BTU boiler, that's not going to be large enough. You have to be meet or more the heat load indicated in the system design. Second part of that is where it notes system design. The system has to be owned by someone. Someone needs to take legal precedence over this system. Contractor, BCIN holder, or a P-Eng. That's your three options. 4241, the water used to fill the system shall fulfill the requirements for the water specified by the manufacturer. If you were to read the installation manual for the boiler that you are currently selling, doesn't matter who, doesn't matter what, all of these folks are going to list in their manual what they need for water quality. They will list the pH of the water between, 7 and 9 or something like that, or 6 and 9, whatever it's going to be. Everybody's a little bit different. The total dissolved solids, how many parts per million of particulate they will allow in the water. Your maximum glycol percentage that's allowed in the water. All these things have to be done correctly by the manufacturer's installation instructions, required by code. 432. Personnel performing installation shall be trained in such functions, meaning that if you are a contractor and you're doing, you're installing this brand of boiler, train yourself in it. Contact the representative, such as Equipco for various lines. We're happy to do trainings to teach you the finer details of installation of various products. This is required by code. It has to be done. 434. All serviceable components of the heating system shall be installed in a manner that they can be serviced or replaced. What does that mean? Ball valves and unions are your best friends in hydronic systems. We should be able to put this together. We should also be able to take it apart because we need to be able to get access to our heat exchangers, get access to our air separators, clean these things, clean our mixing valves. That's part of the process of a hydronic system is the maintenance of it. It is not a set it and forget it. We do need to get into these systems and clean them up every now and again. Oops, sorry. So that's the start. That's the basics. These are a couple pieces with regards to the code and the details that you need to know. Now, we get into the fun stuff. I talked a little bit about heat loss and that system design. Your boiler has to be sized to the heat loss. The design's got to be done to calculate heat loss. How is the heat loss even done? What exactly is it? So it's what you need in order to conduct it is you need your designed inside design temperature, which you can find in the building code for various cities that you are in. Usually the inside design temperature is going to be 70s or 72. You need your outdoor design temperature, again, found in the building code, where it's going to vary from, 0 degrees Fahrenheit to minus 10 degrees Fahrenheit, depending on where you are in Canada. You need those two numbers. Then you need your R value, or your insulation value of the windows, walls, ceilings, and floor inside the home. And then you need your magic formulas. Magic formulas, very easy. Q equals A times U times delta T. Don't panic. This is going to be very, very simple. All it is essentially is a little bit of math. And it's not even hard math. I'm not going to ask you to go through bed math or anything like that. It's quite literally this times this times this. And that's how you're going to be operating this guy here. So let's just kind of break one down and do an example. Q equals A times U times delta T. Let's give you an example. A 10 by 10 wall with R20 insulation and an outdoor design temperature of minus 22 Fahrenheit, which is extremely cold. It's like Hudson's Bay area or up in Nunavut or Northwest Territories. That's where you're going to have outdoor design temperatures of that cold. So let's do the math. A 10 by 10 wall has an area of 100. That's 100 square feet. Then you have R20. In order to find your R value, or sorry, your U value is 1 divided by R. So U value is 1 divided by 20, which is 0.05. Multiply that by 92, which is our temperature differential between 70 degrees inside minus 22 degrees outside. And then you do the math. 100 times 0.05 times 92. So you have a heat loss design for that wall, that 1 10 by 10 wall of 460. That means it would take that means that through that wall, you will lose 460 BTUs per hour. If you had a room where you had these 4 walls and you did all of them, your heat load for the one room was, let's just say it was 1500. You would need 1500 BTUs. Sorry, that room would lose 1500 BTUs per hour that you need to replace with heat from an air handler, radiators, or radiant or something like that. Then you get into windows and doors. Windows and doors use the same formula. You just need to kind of extrapolate them from the wall. So let's go back to that same 10 by 10 wall. 10 by 10 wall. This time we have an R24. We have a 2 by 2 window on this guy here with the U value of 0.5. The U value on windows is always listed on the sticker on new home construction. If you walk past it, you will see U value of a window. 0.5 is a really good one, and then from that, the numbers just kind of change around from garbagey windows to great windows. If you can find a U value of around 0.5, that's actually a pretty decent window. So all we do is we remove the window from the wall and do its math first. So we have a 2 by 2 window, 4 square feet. We have a U value of 0.5, and we have a temperature differential of 92 again, minus 22 Fahrenheit, 70 degrees inside. 4 times 0.5 times 92, 184. So it's 184 BTUs leaving through that window. Our wall is now 96 square feet, so we have 96 times 0.04, because the R value did change in this calculation here, times that by 92, our temperature differential from 70 to minus 22. And that math is 353.28. And then to figure out for the entire wall, we just add them together. So 184 plus 353.28, 537.28. And that's your standard wall with a window in it. That's your heat loss for that wall. What you can then do from that, if you so desire, is you can do a whole home all at once. Provided that the wall insulation and the window U values are about the same across the home, then you can just do the whole thing to get you a good close estimate. This one I did, for example, this was a 1,200 square foot house. So the wall area that we had was 3,960 square feet of wall area, and the entire home was insulated at R24. The windows, the whole window area of the complete house was 40 square feet. All the windows had a U value of 0.5. Outdoor design temperature, we're sticking with minus 22 Fahrenheit. Indoor design temperature of 70 degrees, and we do the math for all of them. So we have the entire math of the area, 3,960, times our U value of an R24, times our delta T of 96. We have 14,572.8 BTUs leaving through all the walls inside the house. Window area of 40 square feet, times our U value of 0.5, times our delta T of 96, 1,840 BTUs through all the windows in the home, which gives a grand total for the whole home of 16,500 BTUs for the whole home. Now, I didn't include the ceiling on this particular heat loss calculation, but that is something that needs to be taken into consideration when you actually are doing one of these things for real. Thing about it is, ceilings and attics usually get insulation very, very thick. Like I've seen R40, R70 in ceilings and attics, so it's usually a very, very small heat load through the ceilings. So it's usually not a huge factor in this one here. One thing to take note of is that when we did this whole home heat loss of 1,500 square feet, we only had a 16,500 BTU heat loss, which is very small. And I want you to think, can you even think of a furnace or a boiler that has a heat loss of, that has a heat output of 16,000, 17,000 BTUs? Very, very unique situations possibly, but for the most part, you're going to have to design a system that will give you this sort of BTU output without short cycling and destroying the system. So from that, now we have our basic understanding of how to do a heat loss. Now let's talk about basic universal hydronic formulas. And there's a couple of terms in here that I want to make sure that we're all completely aware of. We'll start at the top, work our way down. GPM. GPM is the fluid flow rate in gallons per minute. GPM comes up all the time in hydronics. That's our flow. How fast is our water going? Do we need to move the water at 5 GPM or 10 GPM or in most cases 1 or 2 GPM to heat the area? How we calculate GPM is BTU divided by brackets delta T times 500. Your delta T is your temperature drop across your piping circuit. It's usually 10 degrees in radiant inflow and 20 degrees in pretty much everything else. So your GPM, which is equal to BTU divided to GPM equals BTU divided by delta T times 500, that's your standard calculation for calculating flow to deliver a certain amount of BTUs. BTUs, how do we calculate how many BTUs are getting delivered? BTU equals GPM multiplied by brackets delta T times 500. So here's a bit of bed mass for you. Brackets, exponents, division, multiplication, addition, and subtraction. So you will have to do the brackets first on a couple of these guys here. But that's, that's your standard mathematics. So to calculate how many BTUs are getting delivered, you use this formula. And again, your delta T is between 10 and 20 if it's inflow or it's a standard heat emitter. Now that last one that we got here, your delta T equals BTU divided by GPM divided by 500. And that's you can calculate what your delta T is inside of a system. Now these are all for systems that are already existing where you're reverse engineering how to get you where you want to go, or usually it's used for calculating how many GPM you need to deliver heat into a system. But one constant that you see here is the number 500. Let's talk about where that number 500 comes from. Okay, we talk about gallons a lot in hydronics. Now gallons come in a weight measurement. So weight measurement is 8.33 pounds per gallon. So we have that pound of water times 60 times 1. Now the reason that we have even that 8.33 there in the first place is the definition of a BTU. It takes 1 BTU to heat 1 pound of water 1 degree Fahrenheit in 1 hour. But again, we don't do anything in pounds, we do it in gallons. So there's why we had to change that mathematics to reverse engineer that from pounds into gallons. So you have 8.33, which is 1 gallon, times 60 times 1. 1 being the specific heat carrying capacity of water. So you can do that 8.33 times 60 times 1. I think the number is 499.96 or something. If you're at home, try it. It'll be a great time. Now, the 1 changes depending on the water. And the water is not always 100% water. Sometimes it's a glycol mix, and that's where that 1 is going to change. Let's talk about this. If you are talking about a glycol with a 25% solution, you're no longer multiplying that number by 1. You are multiplying that number by 0.94. So it's 8.33 times 60 times 0.94. That'll give you the BTU output at 25% glycol solution. Now looking on the map here, let's pick on 2 of these numbers. Let's pick on 40% glycol and let's pick on 50% glycol. As you see, we're no longer multiplying by 1. We no longer have 100% heat output. Glycol decreases the heat efficacy of the fluid medium transferring that heat through it. So at a 40% glycol, you have a specific heat now of 0.89, meaning that we've lost 11% of the heat efficacy of that water solution. So we need to oversize our pumps and oversize our boilers to get us where we need to go. At a 50% glycol solution, we have decreased the efficacy by 15% right off the top. So that 100,000 BTU boiler is only going to be giving you 85,000 BTUs. You can't move that extra 15,000 BTUs through it because the glycol solution will not carry any more heat than that. Specific heat plays by the rules of physics. Pretty hard to argue with physics. It's just the way it is. So the most efficient way to move that hydronic system is 100% water, but we're not crazy. We understand that there's snowmelt systems and reasons for glycol, but these are what you need to know about. The more glycol you add, the less effective a system becomes. Not the less efficient, it's still same efficiency, but the less effective. There's a difference there between the heat carrying capacity of these 2 water solutions. So that leads us now into what your standard boilers are. So your standard boilers are going to be, you have a condensing type, and you have a non-condensing type. Condensing type you're going to find primarily in residential homes. That's going to be the vast majority of your boilers. Essentially, what you need to know about a condensing boiler is that you want it to sweat. You want it to condense. This is how you get those 95, 96, 97% BTU outputs, is by playing with a condensing boiler. And this is how it does it. For every gallon of condensate that you produce from that boiler, you get an additional 900 BTUs output, 90 BTU output per gallon condensate that it creates per hour. So if you make this thing sweat 20, 30 gallons per hour, that's 3,000 BTUs that you're adding to the heat output, which is a considerable amount of BTUs being added to these systems. So how do you make it condense in the first place? You make it condense by condensing the flue gases. You do this by bringing back cool water temperature, anything beneath the 135-degree Fahrenheit mark. That's how you make these boilers condense. The more condensate you create, the more BTUs are added to your heat output of the system, the higher the efficiency of these boilers get. The burners itself was only about 89 to 90%. The 90 plus all comes from condensation. If you don't make the boilers condense, you are not going to have that high 95, 96, 97% output. The heat exchangers are designed to see condensate, which is going to be mildly acidic. It is mildly acidic because our atmosphere is about 80% nitrogen. That nitrogen, through the condensation of flue gases, turns into nitric acid. It's a mild acid, about the same of orange juice, roughly, but that's going to be about as acidic as it is. Stainless steel heat exchangers, aluminized heat exchangers can deal with condensate all day long. That leads us to our non-condensing boilers, where we're going to have cast iron heat exchangers, copper heat exchangers. These things are not designed to handle anything acidic. So if we put acidic condensate over top of these burners, over top of these heat exchangers, it is going to eat through those heat exchangers. It's going to eat right through them. It's not going to happen, in 24 hours or anything like that. But over time, depending on how much condensate you're creating, you will cause a leak in this heat exchanger. And if it's leak caused by condensation, it will void the warranty. You will not get warranty on that heat exchanger. So for non-condensing, you want that return temperature to be nice and high, anything over 140, 145, 150, something like that. So a good way to think about it is a condensing boiler is extremely good at low temperature applications, which is the future of hydronics starting yesterday. And non-condensing, you want to see more your high temperature applications, such as air handlers and radiators, where you want that 160 to 180 input to get the BTUs that you want. Now, times are changing and we're using much larger rads and much larger heating coils in our air handlers. That'll give you more BTU output at lower temperatures. But a good way to think about it is what is happening today versus what is going to happen tomorrow. Right now, what we have today is to get those sort of systems to give the same output at lower temperatures, much larger, much more expensive. Maybe they can't do that. That's where non-condensing would make sense. But again, you're only going to really find non-condensing available now in commercial applications. Condensing is most of your home applications. So a bit more detail, basically to kind of just reiterate what is kind of mentioned here. Your condensation occurs when the temperatures are below 135 coming back. Non-condensing, you want to make sure that your return temperatures are above 135. That's how you make sure that we get the units to operate properly and as effectively as possible between condensing and non-condensing. There's going to be some differences in the venting applications as well, but for the most part, that's going to be your main criteria as to why a non-condensing or why a condensing boiler is used in an application. So now I've got a little video here that I'm going to show you that it's going to run you through two standard high efficiency condensing heat exchangers. The first one we're going to do is a fire tube heat exchanger. And we're going to watch this video and I'm going to talk through it to kind of show you a couple of the features as it's happening. Most fire tube heat exchangers now are made by a company called AIC, wonderful heat exchanger. Most of our manufacturers of all boilers use these things now. Here comes down our spacer plates. This is what kind of separates our fire tubes. Here they come right down there and right now. That's where our flue gas is going to be coming through. And here's our shell coming across. The shell is what holds the water. The tubes that went down, those are our fire tubes. That's where our flue gases come from. Our base pan is stainless steel, which it can handle that condensate. So it's all designed as a good package to operate during combustion. Here comes our burner. We are a down-fired burner on these fire tube heat exchangers. And we're going to be able to walk you right through what's happening in here. So here comes the cold water into returning. We're beneath that 135, so we are going to be condensing. we're coming up, we are starting to heat from the bottom up. So we are using the coolest water to pre-warm that water. As we move up inside that heat exchanger, the flue gases are hotter and hotter until we get our output temperature desired as we want. Now, here we're going to be flame. We're going to go right down this fire tube. So I'm now flame. I'm going to turn into the flue gas. I'm going to go right down this fire tube. I'm going to be interrupted by these little nodules on the side here to slow down that flue gas moving through. As I slow down, I'm stripping all my heat away and I start to condense. There's my little water droplets. The condensation comes out of the bottom. Again, it is mildly acidic. It gets picked up inside of the drain pan at the bottom, or the collector, whatever you want to call it, and that's designed to evacuate that condensate into one side and have your flue gas transfer over to the other side, up and out. And that is your standard fire tube heat exchanger. A couple things to note: extremely low head loss or friction loss through one of these guys. It is a real big open chamber. Water can flow through it quite easily. Does an extremely good job of heat transfer and is made to last a very, very long time. That's your standard fire tube heat exchanger. Now this next one, fire tube. Now this next one, this is going to be your water tube heat exchanger. So we see there on the left, that's our burner and our plate. On the right of that picture, that's our actual heat exchange. That's where the water is going to be coming in from. One thing to note is that what they've done to create a water tube heat exchanger is they've taken a 3/4 inch round tube and they've ovaled it. So it creates a higher head loss, meaning that it has to be piped in a certain way to overcome the high head loss of the boiler itself. The thing about it is that they're very, very easy, extremely easy to take apart and clean. Where a fire tube is a bit more complex to take apart and clean, fire tubes are very, very easy. So let me walk you through it in a real quick video. Our water is going to be coming up. It's in a primary, secondary piping coming up, and it's going to be getting heated through that water tube heat exchanger. Getting heated because our burner, which you're going to see here in just a moment, is coming in and is blasting that heat, and the heat transfers in between each of these individual coils. So when you're cleaning one of these fire tubes, it's designed to be cleaned in between these slots. It's not just one big open chamber, it's actually individual lines as we transfer that heat through that. So cleaning it's going to be taking a little bit more time, but it's a really good job of heat transfer. They each have their pros and their cons. Fire tube, extremely low head loss. Fire tube, a little bit more difficult to clean. Water tube, higher head loss, might require a couple extra components, but very, very easy to clean and very fast and quick to take apart. So we're not here to pass judgment on other. This is just the main two that you're going to see in the vast majority of all the quality boiler makers that are out there right now. There's a few other heat exchangers that are used in the Asian boilers that come out right now, where they're a down-fired, kind of like a heat exchanger, but they don't quite have the same details as these fire tube and the water tube. That, and they haven't caught on nearly as much in the North American market. These are the two that you're likely going to find on job sites and in most boilers here in this existing marketplace. Okay, so we talked about condensing versus non-condensing boilers. I talked to you about standard condensing heat exchangers. Now I want to talk to you about pipe size. Pipe size is extremely important, and we want to make sure that we get it right. Because if we put our pipe too small, we're not going to carry the heat out of the system. So I'm going to go back and I'm going to pick on that 100,000 BTU boiler. Now on the left of this chart, you have pipe size. Across the top, right after flow rate, you have delta T. As I mentioned before, your standard delta T's that you're going to find in a system is going to be 20 degrees for radiators, air handlers, indirects, everything like that. So we're going to pick on the 20 degree delta T. With a 100,000 BTU boiler at a 20 degree delta T, what size pipe do I need to carry that heat? If you look here, at a 20 degree delta T, we don't get over 100,000 until we hit the 1.25 inch pipeline. Now, the way that this operates, or the way this works, is that we have this pipe size because we know that when we're moving water through this pipe, we're going to be under 4 or 5 feet per second, which is the speed limit of water in a hydronic system. 5 speeds, the absolute max. 4 feet per second is what we like to see. So at a 20 degree delta T, 100,000 BTUs requires 1.25 inch pipe. And this chart can be extrapolated to figure out exactly what size piping that you need. And this is not to say that the 1.25 inch piping is going to be required throughout the entire system. We just need that for our mains. Maybe off of our mains, we're going into this branch over here, which is 10,000 BTUs, which only requires ½ inch. And this branch over here, which is your indirect, which requires 60,000 BTUs, which we can use 1 inch. So there's all sorts of different ways to extrapolate which pipe you want to use, which size you want to use. It all just basically depends on what exactly are you doing in your system, and use this chart to help you to size that piping properly. You also have, and this is not my numbers here, this is put out by the Piping Institute, your maximum flow rate through piping. You have copper pipe and steel pipe. For what it's worth, copper pipe characteristics are extremely similar to that of PEX. So they're roughly the same. And you will see we have maximum GPMs that we can put through these piping systems in order to not overflow these pipings. So when we overflow them or flow too fast, we cause degradation to the inside of the piping. So for example, that 1.25 inch piping that I was talking about, it is a max flow rate of 14 gallons per minute that we can put through this piping here. The 1 inch max flow of 8 gallons per minute. And again, I'm talking about the copper pipe size because copper is much more common nowadays than steel. But you can see what is the maximum amount of flow that you can do. When you go back to your universal hydronic formula of BTU equals GPM times delta T times 500, you will then see what sort of GPM is required to carry what amount of BTUs you want to put into a room. So if you wanted to do the math and you figure out that you need 4 GPM, you know, that 3/4 inch pipe is 4 GPM is the maximum that we allow by 3/4. Maybe you want to upsize to 1 inch, maybe you're fine with 3/4. But there's going to be options for you, and these charts are designed to give you this information as to max BTU carrying and max flow rate through these pipings. Now this next video I have for you, it's a little long, but it's an extremely good video. It's going to talk about the actual how to size a pump and how to work with that. Now I got to go back here for just a moment because I need to turn on my audio because I didn't do that when I started, and I should probably do that. There we go. My apologies for there we go. So now you're able to hear the video, which is going to be great. Now this video is going to show you how to read and work with a pump curve. We talked about how you can figure out the GPM required. I want you to keep that one in mind for GPMs for now. The other thing that's going to start to come up in our conversations is what's known as head or friction or head loss. That's going to be the second part to this detail as to how exactly these pumps operate and how they work. So without further ado, we're going to watch the video, and then I'm going to take a bit of a deeper dive into head loss and exactly how that works inside of a hydronic system.
How to read a pump curve 101. This video was created to help the HVAC professional install and maintain TACO equipment. Please read the on-screen disclaimer before viewing this video. Knowing how to read and interpret a pump curve is important to any HVAC professional. Whether you're a residential installer working on a hydronic home heating system or an HVAC engineer designing a large, complex commercial system, you need to understand pump curves to select the right size pump to meet the requirements of your system. This video covers the basic information on how to read a pump curve based on pump head and flow. A pump performance curve, usually just called a pump curve, is a graphical representation of the performance of a pump based on testing by the pump manufacturer. Every pump has its own curve, and those curves vary widely from pump to pump. The variations depend on many factors, such as the horsepower of the pump and the size and the shape of the impeller. Pump curves can be used to provide information on many other elements of pump performance. Some of these are of interest only for designing commercial systems. We'll cover these in another video lesson available on the TACO website. In the simplest and most widely used form, a pump curve shows two vital pump performance factors, flow and head. Flow, measured in gallons per, is the rate at which water must be moved to carry heat throughout a hydronic system. Too much flow results in system noise. Too little flow means insufficient heat will reach at least some areas of the building. Pressure is usually measured in PSI, pounds per square inch. But in hydronics, we calculate pressure in terms of head pressure or head loss as measured in head feet. Technically, head is the total mechanical energy content of a fluid at a given point in a piping system. A circulator has to produce a sufficient pressure differential to overcome the pressure or head loss created in the piping by friction and by the various valves and fittings in the system. Converting PSI to head loss is very simple. A column of water 2.31 feet or 28 inches high will have a gauge pressure at the bottom of 1 psi. Therefore, 1 psi of pressure drop in a system equals 2.31 feet of head. Let's see how these two factors look on a pump curve graph. The curve enables you to see how this pump will perform at any given point within its performance range. You can see, for example, that at a flow rate of 10 gallons per minute, the pump will produce between 7 and 8 feet of head. Or you can look at it the other way around. At 4 feet of head, this pump will generate a flow rate of just about 17 gallons per minute. Reading the pump curve makes it easy to choose a pump for a particular hydronic system. Technically, if the head and flow operating point of your system is located on or below a given pump's performance curve, then that pump will be sufficient to do that job. So if your system requires a flow rate of 12 gallons per minute and a head of 4 feet, the 007 will easily meet those requirements. It will also meet the system requirements if you need a flow rate of 6 GPM and a head of 2 feet, or 5 feet, or any other intersection of flow rate and head in the area below the curve. Here's a graph showing the curves for the various models of 𝘬𝘳𝘬𝘳 circulators. Using our same example of a system that requires 12 gallons per minute flow at 4 feet of head, we can see that several models of circulators will meet those requirements. The 0010, or the 0011, or the 0012, and the 0013 too. As you can also see on the graph, pump curves can be very different for different pumps. Here's the curve for a 𝘬𝘳𝘬𝘧 circulator. You can see that this pump can generate much higher head than the 007, up to approximately 35 feet of head. But the 009 can only produce a flow rate of just about 10 gallons per minute. We say the curve for the 009 circulator is a steep curve. The 0012 has a very different shaped curve. This pump can produce a lot of flow, up to 52 GPM according to its curve, but can produce a maximum of only 14 feet of head pressure. We call this a flat pump curve. It's helpful to think of 𝘬𝘳𝘬𝘬 fixed speed circulators in terms of families that are grouped together by their curves. The 005, 007, 0010, and 0012 circulators are all members of the flat curve family. As you can see by their curves, they can produce high flow rates but relatively low pressure. A smaller flat curve pump, such as the 005 or 007, is ideal as a system circulator for zone valves in standard residential jobs or as a zone pump. The larger flat curve pumps, like the 0010 and 0012, are designed for larger residential jobs or light commercial applications. On the other hand, models 008, 0011, 0013, and 0014 are all in the steep curve family. Compared to pumps with a flat curve, these circulators can generate a lot of head pressure but comparatively low flow. These circulators are best for higher head applications such as high head loss fan coils, air handlers, and heat exchangers. A third family is small but worth mentioning. It includes the 003 and 006. Both these circulators are designed for domestic hot water applications. That leaves the 009, which is in a family of its own. This pump is specifically made for solar applications. That covers fixed-speed circulators, but we also need to look at the curves of two other types of circulators used in residential jobs. The first is the 3-speed pump. This curve is for the 𝘬𝘳𝘬𝘬15 3-speed cartridge circulator. The curve for a 3-speed pump actually consists of 3 separate curves, one for each of the pump speed settings. The pump can operate on any one of these curves, but not between them. That brings us to TACO variable speed 𝘍𝑇 circulators, which are different from all the pumps we've talked about so far. Here's the curve for the 008 VDT. It looks the same as the curve for any fixed-speed circulator, but you read it very differently. A TACO VDT circulator operates on its own curve, just like every other pump. But it also operates at any other point below the curve, depending on the needs of the system. In contrast, this 008 fixed-speed pump can operate only at points along its curve, not above or below it. The pump has no choice but to operate on its curve, and it doesn't matter what head and flow the system needs at any given moment. But the VDT variable speed pump can and does operate anywhere within the shaded area, depending on the specific immediate flow and pressure needs of the system. In other words, a fixed-speed circulator forces the system to work on its curve. A TACO variable speed circulator adjusts its curve to meet the needs of the system. Now you have the basic information that you need to read pump curves and use them to choose the right pump for any residential job. But there is still more information on the TACO website, plus a handy tool for finding pump curves. It's called the Pump Selection Wizard. Just put in the head and flow rate of your job, and the Pump Wizard will show you all the TACO pumps that meet those requirements.
So yeah, we're going to stop the video there. Long and the short of it is, I just want to give you an overview of what a pump curve even is. Like, what do these things even look like, and how do you use these things? Again, it all goes back to the heat loss. Heat loss, you're going to tell me how many BTUs I need to put in an area. Once you know the BTUs, I can calculate how many GPMs I need to put that amount of heat in the area. And then I get into the final part of it, which is calculating the head loss through my heat emitter. Heat emitters, again, your radiators, your air handlers, and your radiant inflow. So those are all going to have their own charts with regards to head loss, which I'm going to show you here in just a moment. But there's also the pipe in between that has its own pressure loss. So let's just start up at the top because it's nice and easy. It's a really easy one to read. Let's start at the very top one. This is type K copper, 5/8 of an inch. When we move 3 GPMs through 5/8 inch type K copper, we get 0.026 psi per foot pressure loss. Now then we can extrapolate, we can use the math to convert PSI to feet of head and see that we have, that's going to give me a 0.01 feet of head per foot. And I've got 30 feet of that pipe. It's like, okay, now I've got, 10 feet of head, and I need to do 3 GPM. This pipe's going to give me 10 feet of head. Okay, that's my flow rate. That's my pressure loss through my distribution piping. That's going to be step 1, is figuring out your head loss or your distribution piping. If you don't know how to do this, you're not super comfortable, there is some cheater methods that you can use. We can talk about that in person someday. But just know there's charts out there, and we all want to help you to make sure that we get it done correctly. Use the charts, know your GPMs, figure out your PSI per foot, then convert that into feet of head. There's all sorts of ways to do it, and we're all here to help you get that done. But that's calculate your head loss through your distribution piping. Your next one is going to be calculating the head loss through your heat emitter. So let's really hop in here. So this is my heat emitter. Let's go back and pick on that 16,500 BTU house that we were talking about. It's like, okay, so we look through our chart. We want to be underneath that 135 degree mark. We still want to heat that 16,500. Okay, here we go. So we heat 130 degree water at 4 GPM. We get 16,500 BTUs. Perfect. That's exactly what we want. So then what is our head loss? Our head loss is right over here. So this is water pressure drop, feet of water columns. This is going to be in PSI. So you need to be at 3.87 and convert that over to feet of head. And I need to move that water at 4 GPM. So I can go back and be like, okay, I'm at 4 GPM, move through type K. My distribution piping at 0.047 PSI per foot. Okay, awesome. And then I go to my unit here at 4 GPM and need that additional 3.87 PSI and then convert that whole thing into head. And then I go back to my pump curve. I find something that is 4 GPM at, let's just say it's going to be about 12 feet of head. And that's how we size our circulator for our heat emitters. Quite simple once you've done it 100,000 times like I have, but I can understand that this might be a little confusing for you on your first time. Basically, what I'm asking you to do, use the charts. They are your friends to at least tell you your head loss through your heat emitters, and you can figure out your distribution pipe kind of afterwards. But these charts will give you your BTU output, and I can't stress this enough. The only way to know that we've got the unit sized right is by doing that heat loss and knowing exactly how many BTUs we need to put back into that home. So that's where that heat loss really comes from. So this is an air handler chart. This is a chart now for this is slant fin baseboard radiators. This is going to be the same as, you know, pretty much anybody's, but it's going to be very similar. So go back to remember that first room that I did. We had that one wall that had a 480 BTU heat loss. Okay, so let's play with that. I'm going to use the coolest water I can on my chart, which is this one here. The chart starts at 140. I know that at 4 GPM, which I like that number, it's nice and easy, we have 340 BTUs per foot. The room itself had a heat loss of 480, so I'm going to need 2 feet of baseboard to get where I need to go. Yeah, it's a little oversized, but that's fine. At least we're not undersizing it. So then we need to know our pressure drop. Now, some of these forms are going to be noted here in milli-inches per foot. Milli-inches per foot is a unit of measurement. Kind of drives me a little nuts because it's about as close to 0 as you can get without being 0. Essentially, what you need to know is that for baseboard radiators, it's going to be essentially just the copper tube size that's going to be going through this. So you can use your 3/4 inch or 5/8 inch piping head loss chart to figure out your head loss through these guys here as well. Because again, these milli-inches per foot does not translate well into PSI or into feet of head. Other heat emitters give off different charts, like your panel radiators. Those have a different head loss from your air handlers, which I just showed you. And then finally, you have radiant for radiant inflow. Now, I know everybody thinks that they love radiant inflow, and you're right. It is a very, very comfortable heat, very nice heat. Takes a little bit longer to install, but it is also extremely finicky, we will say. There are so many variables on the heat output of radiant systems that all I can give you as far as this training presentation here is concerned is ranges. I can give you estimates. So what I'll tell you is this. You are looking at a system that will give you approximately, I'm going to pick on the 1/2 inch PEX tubing length here because that's most common, approximately 22 to 30 BTUs output per square foot. So that's what you're going to be looking at. You have a suggested flow of about 0.6 GPM per loop, a max circuit loop of 300 feet. This is all going to be subject to the design and installation of the system. If they're putting it on little installation board like you see here, yeah, probably gonna be closer to 22 to 24. If they're putting it in those radiant panels with the little pucks on it that you can fit through, those would be 22 bang on, maybe only 21 maybe, because you're losing a bit of the surface area contact from the PEX into the gypcrete or concrete overpour. If you're using heat transfer panels, the aluminum panels, you could be 30 BTUs per square foot up to 40 BTUs per square foot. There is no rules with Radiant. Radiant is the only system that truly needs to be designed in order to maximize comfort. It is very susceptible to the installation details that you are putting in with it. So it really should be designed with someone who understands and can calculate the BTUs that are required and then can reverse that into the actual flows required. That can tell us how to balance our manifolds, how to calculate our loop lengths, stuff like that. I'm not saying Radiant's bad, not by any means. I'm just saying it is the only system where there is no cut and dry numbers with regards to how many BTUs you're going to be getting out of it. It is very susceptible to the installation details. Ton of variables to consider, such as the gypcrete overpour, or is it going to be heat panels? Then we also have, with regards to Radiant, our staple up, where we're going to be going in the joist space on the floor underneath to heat the floor above us. That has a tremendous difference than putting the PEX tubing right in the floor of the room that you're in. It needs to be ran at a hotter temperature. Heat transfer panels are now nearly required. They're not exactly enforced, but they're extremely good idea because you need to transfer that heat over a much thicker, not so much thicker, but much harder area to transfer heat through, which is wood and carpet, and which leads you to the last point, floor coverings. Carpet's going to require a hotter water temperature and a hotter floor temperature than, let's say, tile. And tile, similar to hardwood, is going to have a maximum floor temperature that you can even get that to without damaging the tile or warping the hardwood. There are, again, so many variables with radiant that I highly encourage and strongly recommend that when you're doing a radiant system, get that one designed. Don't just guess at that one. If you do, you can do more damage to a system than good by overheating it and cracking tiles and warping floors. Then the homeowner would have any idea than what they're in for. So just make sure that you're aware and educated as you can on radiant systems, and then do a little bit of work with the contractor and homeowner as well. That it's not just, you know, put a bunch of piping in the floor and away you go. There is variables to a radiant system. Okay. Next one that we have online here is water quality and the importance of water quality in a hydronic system. As I mentioned at the beginning, water should be clear inside of a system. Clear, or it should be colored the same color as your glycol solution. It should not be black. It should not be brown. It should not be sludgy. It should not be sandy. None of that stuff. It should be clear. It should be easy flowing. And there's a couple pieces that we're going to talk about that are required to go into a hydronic system to make sure that our water stays as clear as possible. But first, let's talk about what is the bad stuff in our water. The worst color hydronic water that you can see is going to be black. When we see black, we know that's going to be the incorporation of magnetite. I want you to think of magnetite essentially as like a liquid metal. It is an extremely fine particle of ferrous metals, so it's going to be magnetic or stick to a magnet, and it's going to stick to any hot surface inside of a hydronic system. Hottest surface inside of a hydronic system is going to be the heat exchanger for the boiler, and your magnetic portion is going to be in your pumps. So it'll stick to your heat exchangers and it'll stick to your pumps. That's your magnetite, and that we really want to get out of a system because it's going to cause detriment to our two most important parts. If we don't heat it, then we can't get the heat out of it. We're not going to heat our home. And if we can't flow it, we can't distribute the heat, so we're not going to be able to heat the home. Magnetite is the very first piece of a system that's going to go cataclysmically wrong, and the only way to get that out is with magnetic separation. So that's one thing to keep in mind with regards to the trim that we're going to be talking about. So I talked about before, you know, we had the buildup of the magnetite or dirt or calcium or anything on the system will lead to a low flow situation on our heat exchanger. If we can't move the heat through that heat, or move the water through that heat exchanger, we can't scrub away the heat. If we can't scrub away that heat, we're going to get hot spots, and we're going to lead to cracks in our heat exchanger, cracks in our pipes, stuff like that. So here's a little picture of a heat exchanger. This is a water tube where we had a big buildup of magnetite on the inside, led to a hot spot, which led to a crack on the heat exchanger. This was not a warranty situation. The homeowner had to pay full pop for a new heat exchanger because the water quality is bad on this one here. So that's magnetite. Your other side of this conversation is the stuff that is non-ferrous, which is your, well, for starters, your calcium, magnesium, lime scale buildup. Here's a little chart that we have of the hardness of water across North America. Well, it's exclusion of Mexico, but it's through Canada and the United States. Canada doesn't have, well, I'll talk about Ontario doesn't have terrible bad water. Lower Quebec doesn't. Out in the Prairie provinces, extremely hard water. You could chew that stuff if you so desired, and that needs to be addressed because we have what's called mineral salts, and these mineral salts are your calcium, limes, and your magnesiums. I'm going to talk about that here in just a moment. But let's just first talk about the conductivity of water inside of a system. So you have conductivity building up inside of a system let me start again. Anytime that you add heat to water, it becomes electrically conductive. That's just physics. Again, you can argue with physics all you want, but it's going to win. So when we have electrical conductivity in our water, we're going to have buildups of these magnesiums and calciums, and that'll start to pit and eat away at these systems or create little mounds of, you know, calciums, limes, and stuff like that, which will lead to pitting on the inside of a heat exchanger. Pitting is then eventually going to lead to your leaking on the inside of your heat exchanger or pitting and pinholing in pipes. So that's just number one stuff that is going to happen with regards to these ferrous materials, these other materials inside of water. So what I want you to think about is that water is like a conveyor belt. It's just designed to move that heat that you created in the heat exchanger, created in the boiler, and send it to that heat emitter where it's going to give off its heat and then the water is going to come back to the boiler, get reheated. So it's a conveyor belt, just keeps on moving around and around and around. Now inside that water we have these mineral salts. That's what they're called. Like your calcium ions are called salts. So calcium ions, magnesium ions. What happens is these salts become less soluble, meaning that they come out of solution as the water temperature rises. As the water temperature goes up, these mineral salts come out of solution and they start to stick and create deposits on any metallic and non-metallic surfaces, but just as long as it's hot, they like to stick to that. The hotter the area, the more it's going to come out of solution, the more buildup you're going to get inside of those areas. This is why scale is formed on the inside of heat exchangers. It's the hottest area of the system. It's where all of these salts are going to come out of the solution, and it's where the calcium, magnesium is going to flake and accumulate at the bottom of our heat exchangers. It's extremely detrimental to the output of the boiler. It's not going to work as well. You're not going to flow as well, and it's also not a warranty situation. So you need to treat that water first to make sure that we get the mineral salts out of there, or not let them go in the first place. So basically what you have, so all these sulfates and calciums and all this stuff, you know, these are referred to as basically your water hardness. There's also iron in water, which is your ferrous material, which can lead to that pitting, as I showed at the beginning of this piece here. But these guys here are going to lead to your scale buildup. There's a bit of a difference between iron buildup and scale buildup, but essentially they're all going to be inside of that system, not allowing for the best water transfer. So if we have hardness inside of a system, or hardness in your water, we got to get that out somehow, because if we don't get it out before it goes into the water in the hydronic system, it's going to come out as soon as we turn the hydronic system out. Sorry, turn the hydronic system on. And that is not what anybody wants, because that's going to lead to a low flow application. So this is basically just talking about the how they kind of come to be, positively and negatively charged ions, and how they will stick to each other and start to create more and more abundant little deposits as these little ions move about inside the water, and how that sticks to the inside of these heat exchangers. I showed you on the fire tube how it accumulates on the inside of that one, and this is how it accumulates on the inside of a water tube heat exchanger. Fire tubes are more forgiving to bad water quality, where these water tubes, that's a very small water chamber going through there. So any sort of buildup will lead to a low flow application, and you're going to crack your heat exchanger very, very quickly. And again, that is not going to be a warranty replacement. That's going to be something on the homeowner that they need to pay for. Here's a visual representation of exactly what's happening and why we crack heat exchangers. We get the buildup, as you see there on the right-hand side of this picture, the buildup of this scale is going to be inhibiting the scrubbing of heat away from our flame. Our flames over here, you know, we're burning natural gas. The flame temperature is sitting there at around 1800 degrees, probably closer to 2000, but let's just say it's 1800 degrees. The water needs to move through on the other side of that heat exchanger to scrub that heat away. At 1800 degrees, it does not take long to warp and damage metal. I don't care if it's stainless, I don't care if it's aluminum, I don't care what it is. It doesn't take long to warp metal at that sort of temperatures. So the buildup of scale now acts like an insulator. If the scale's there, it's insulating that piece of steel against the water's not touching it, so it's not able to move that heat away. And that's what leads to the blistering and eventually cracking of a heat exchanger. That's what it's going to look like. There's a couple different ways that you can treat hardened water. Most common solution that you see out there, let me say this again, the perceived most common solution that you will see out there is just by adding a water softener or filling the system with softened water. The problem with softened water is that, you know, you're adding some sodium into that system, which is going to be extremely receptive to the electrification of, you know, when you heat water, you generate small amounts of electricity, and it's going to lead to those becoming even faster happening with our buildup of our scale deposits. So although it's softened water, we now are extremely electrically conductive of that system, which can lead to failure of your galvanic components or your galvanized components, such as, you know, your volutes of your pumps, the galvanized finishing on some heat exchangers, stuff like that. So softened water is not exactly the solution. Yes, it removes the sodium and the magnesium, but it replaces it with something that's not as detrimental, but it can be over a long enough time. So softened water is not the best solution. The best solution is for you to actually use demineralized water, where we've taken those sodium ions, your magnesium ions, your lime, stuff like that, and you've replaced those through ion exchange through the demineralization process to leave it with strictly dihydrogen monoxide, or H2O, straight pure water. Demineralized water is extremely good for a hydronic system. You don't have any of that scale to build up, extremely long life, and that's going to lead to a much better solution for you long-term down the road, is by the demineralization. This is basically just a overview of exactly what happens in the demineralization process. Essentially, it's just like a water softener. We're just using ion exchange, but in this case here, we're using the OH particles and the H for our atomic compounds that we're exchanging with it. So it's not putting any sodiums in the water. It's just hydrogen and hydrogen monoxide, and that's going to create your H2O when it reforms together. A note here, this is one of the installation manuals from a boiler. Doesn't matter who, but this is just showing how the details are in the installation manual for what the water quality must be in our systems. So this case here, you can see the pH of this particular boiler must be between 7 and 9. That's it. Your hardness between 50 and 200 parts per million, or 3 to 11 grains per gallon. That's it. Chlorine, 150 parts per million. Glycol, 50% maximum. TDS, or total dissolved solids, 300 parts per million. The only way to hit a lot of these numbers, well, there's a couple ways. Well, there's basically only two ways. Number one is to use demineralized water to get your total dissolved solids and your hardness down to the area where you need it. Also, your conductivity. As I mentioned, softened water can add to a higher conductivity. So demineralized water takes care of your TDS, your hardness, and your conductivity, and that leaves you only with really your pH to worry about. And the only way to balance pH in demineralized water is by using a chemical stabilizer, such as it's listed here on this manual here, the Fernox F1 protector. These chemical compounds have buffering agents in it that are going to buffer the pH down to about base, which is going to be, oh, that's probably not the right word to use, but about neutral, which is going to be about 7. The other thing that these will do is that if there is any particles in the water, any TDS floating around, it will suspend them. It will not let them stick to any of the hot areas. So it's going to keep those magnesium and calcium particles moving through the water. It's not going to let them stick to anything and become larger deposits. So that's really where chemical compounds come in, which makes them so effective as an addition to demineralized water. Now, one thing to take note of here is that the glycol that you get, if you get the pre-mixed glycol, it's going to be mixed already with demineralized water, and the good ones, the really good ones, are already going to come with a stabilizer built into that glycol as well. So you have a couple different options. Essentially what I'm telling you here is that as long as you don't fill your boilers from a tap, you're going to be okay. Take a little bit of time and think about the water going through the system. You've already, the homeowner's already spent thousands of dollars on a boiler. You charge them additional $20 or $100 to protect the water, well worth it to protect that warranty as well. Here's another example from a boiler manufacturer's installation manual, where they say again the pH between 7 and 8.5, and the hardness hardness is to be less than 7 grains. So this is gonna be different. This is the difference between a fire tube and a water tube heat exchanger as to what they will accept. It also goes to point that there is no magic bullet. So there's no magic water that you can put into everything and it'll work, with the exception of demineralized. These things need to be checked and adjusted per each boiler manufacturer's installation instructions. So it is important. Read that, make sure you understand that, make sure the contractor, the homeowner, the builder understands that as well. That shows that you're not just, charging additional $20 to $100 to whatever it's going to be for whatever reason. There's a reason you're doing this, because it has to be installation manual compliant. Then we get into our trim. There are a couple pieces of trim required by code. The only piece that is, literally written down that is required is your high efficiency air separators. A high efficiency air separator required by code, the CSA B214. In order to be a high efficiency air separator, it has to have media on the inside and not just a steel plate with a baffle, media on the inside to create turbulence in that water, where that air bubbles that create when you create turbulence can rise to the top. I want you to, if you're at home, and maybe you got one of these little partially drinking water bottle, you shake it, you see all those air bubbles start to be created in the water. That's because we are creating turbulence. High efficiency air separators create that turbulence, and they have media inside to coalesce those little air bubbles and bring that to the top and burp it out of the system. Only media meets the 214. A plate does not. I want to be clear on that one, because there's some products out there that, you know, claim to have all the bells and whistles, but they do not meet minimum code. So just something to keep in mind. So your next piece on the line, that's your dirt separators. Almost all dirt separators now are both dirt and magnetic, where they can catch things like, well, first of all, your ferrous materials coming off inside of your system, and also your ferrous materials, your iron in your water if you filled it with just tap water, but then you treated it, so it's going to be okay. And then it'll also, with the dirt separators, such as this one here, you're also going to catch the non-metal or non-magnetic or non-ferrous material in the system as well. Now, there's some dirt separators out there that are magnetic only. They will never, ever catch things like Teflon tape, solder balls, flux, plastic shavings from PEX tubing and stuff like that. It won't catch them. So if you ask me, what's the point of them? I have honestly no idea. You know what? I promised myself I wouldn't go on a tangent, and I'm sorry. Let me just try that one again. The reason that you're going to want something that's going to catch the dirt is because there's going to be dirt inside of a system no matter what. The best situation you can put yourself in is by giving it a dirt and magnetic separator, that 1-2 punch, get it properly done, get all the dirt out that is going to be created inside of a system. The last one that you see on the right, that's called a low loss header, where you can get these that are both, or low loss headers, that's called a hydraulic separator, and it hydraulically separates the flow from the boiler and the system. We'll talk about that here in just a moment, but essentially you can get these with built-in high efficiency air separators, built-in dirt separators, and built-in magnetics, where it can be everything you need it to be all in one piece. The less pieces you have, the less leak paths in a system. So as I mentioned, air separators are the only piece that was required by the CSAB 214 code. That's minimum code for you, though. That does not mean that's going to be the best system. I still highly recommend dirt separators. Now, air separators should be installed at the hottest point of a system. If you've ever boiled a pot of water, air starts to come out of solution as the water temperature gets hotter. As you get the higher water temperature, air comes out easier. That's where you want the stuff to come out. So that's where you want these things to be inside of a system. They're going to be on every single system. Usually it's also where you tie in the expansion tank for the most part, but just know that you do need to put them in. It's always best to put them right after the boiler. It should be the very first thing that the boiler sees, where the water is going to be the hottest. The other type of air removal device that you can use, you still need to have it high efficiency because that's required by code, but the other thing you can use is going to be your high point vents, where you put them at the highest point of a system, usually used for the original filling of a system, and then they're not really designed to burp out air exactly after that. They still can, don't mind you, like if you get a little air pocket that's released and it finds its way there, it'll still burp them out. But for essentially, they're really just used for the filling of a system. This is the little diagram here what that coalescing media on the inside of an air separator can look like, where it's got all these little pieces on the inside creating all that turbulence, and then the air bubbles are going to stick together. As they get larger and larger, they rise up inside that air separator and eventually burp out of the top. That's your coalescing on the inside. Dirt separators, that's the pieces that are going to remove your little bits of dirt, your flux, your solder, your Teflon tape, your buildup of little bits of lime and calcium scale that builds up inside of a system, any dirt or sand or anything like that that creates inside of a system. This is where that comes out, is in the inside of a dirt separator. Now, dirt separators are going to be put usually on the last thing back to the boilers, the last thing that it sees. It's a good idea for you, for your dirt separators, to use something that can be flushed, where something like a Y strainer has to be taken apart and cleaned. Flushing is much, much simpler and much easier to go through or to do inside your system. So again, things you're going to see that are the cause of the dirt and debris. You have your pipe thread, your cutting oils, your metal shavings, your Teflon tapes, your flux, your solder balls, your HDPE if you're using that, plastic shavings, if you're using PEX shavings, all that stuff can build up on the inside of a system. And so you want to make sure that that stuff does not get back to the heat exchanger where it can cause problems, or back to a pump where it gets caught in the volute, something like that. It can cause problems to the impeller of your pump. So we like to see it just before the boiler in case you want to have it there so it catches everything. So the heat exchanger is always going to make sure that that one is protected. So here's a little diagram of what it looks like. You got dirt particles in the water. It's coming through. When it hits the dirt separator, it creates a pressure drop. You have big pressure up. It's a great big open area. You get that pressure drop, and then gravity kind of takes over from there. Whatever dirt is in the system, whatever it is going to be less weight than water. So it's going to be pulled to the bottom. If you have a magnet down there, even better, because the magnet is going to pull that magnetic material, such as the magnetite, which is extremely small, all the way down to the bottom to get that out. As it's pulled out, it gets caught inside the dirt separator. You do your flush, and as you'll see, you'll get something that pops out that kind of looks like chocolate milk. One other form of a chemical that you can use in conjunction with dirt separator, it's called a chemical flocculant. Essentially what these things do is that they just congeal materials that are not dihydrogen monoxide. It pulls all the impurities out of water and congeals them. Make it very easy for a dirt separator to catch these things. Now here's a video of dirt separator in action where we're going to be releasing dirt and sand and debris and metal shavings into a system. You're going to be able to see how exactly we capture all that and how easy it is to flush with a dirt separator. Okay, so we had all that dirt in the system caught in your dirt separator. We flushed it at the bottom until all the dirt was removed. Now, how do we know the dirt was removed? Because the water went clear. That's the color that we want. And again, if it's not clear, it's the color of your glycol. That's what you want to see. You don't want to see brown, and you definitely don't want to see black. Okay, so a couple other more different types of dirt separators. You also have your basket or your Y strainers. I hate these things. People never clean them. Don't use these things, but I have to show it because in case you need something, it's the only thing that'll fit. I get it. You can use them. This is what's going to end up happening to them is we're on the right-hand side there. They're eventually going to get plugged and restrict flow back to the boiler, causing a no-flow situation, and it's going to be an error code. If you do use them, please clean them. There is a place and a time for them, but I'm just not a huge fan myself because there is so much better. Last piece inside of this portion here we got is our hydraulic separation. Hydraulic separation, essentially, like I mentioned, it separates the flow from the boiler from our system. Boiler gets its own flow, system gets its own flow. They completely decoupled the flow from the two. The boiler needs to see flow continuously to whisk away heat from a heat exchanger. The system can fluctuate wildly in the flow that it's required, especially in zoned systems. If you have a whole home, a 2,000 square foot home with 5 different zones in it, you can see flow rates as little as 1 or 2 GPM, where the system flow is going to be much less than the boiler is required for its minimum flow. So a hydraulic separator separates everything nice and easy, protects the boiler always. Extremely simple install. Lets the boiler do what the boiler needs to do. Let the system do what the system needs to do. It doesn't matter the flow that each one is going to be requiring at the time. This is a bit more of an advanced piece with regards to the actual how it works and everything like that, but I assure you it makes the simplest of installs to use a hydraulic separator. Very, very easy to install, right from the boiler, right in, right from the system, and out. You should be using these anytime you're doing a re, and for the most part, folks are using these nowadays on all new installs, especially the more higher end ones where they actually protect the boilers and care about the systems. We see these all the time. You're going to be saving money on labor, you're going to be saving money on piping, you're going to be saving money on additional pieces, because on this one here that you're looking at, it has the high efficiency air, high efficiency dirt, and that magnetic built into it all in one, so you don't have a multitude of pieces. And here's a little cutaway. You can see on the inside that media, that coalescing media that creates that turbulence, make air pop out the top, make dirt fall out of the bottom. So where we like to see them, again, right after the boilers. It's from the boilers out and then from the system out. It's just those two little pieces. It just kind of separates it from the boiler side from the system side. That's really where they should be used with regards to the install. And you can put multiple boilers together and just get larger and larger hydroceps to do the exact same work. You just need to size them correctly and properly. Now, I just want to quickly show you here. This is the difference between a standard primary secondary system and a hydraulic separator with regards to how these things are going to be operating. So you got the boiler here, then we're going into a set of closely spaced tees. This is essentially a primary secondary system where our primary loop is in the boiler and our secondary loop is the system. That closely spaced tees is what separates our primary from our secondary. You also see right underneath the boiler, that's a high efficiency air separator. Now, if we were to use a low loss header, we now have a boiler into our low loss header and back. No need for another additional high efficiency air separator in there. We can have it operates on the same dynamic of closely spaced tees of no more than 4 pipe diameters apart, and it ensures that there's going to be a low velocity or low pressure drop between its two flows with regards to which way it's going to be flowing. And here's a great little picture of you can take out the closely spaced tees, your air separator, and your sediment strainer or dirt filter, and replace the entire thing with a hydro separator, and it still makes that primary secondary system, which works extremely well for less fittings, less leak paths, less labor. It's going to be more effective and more efficient for everybody involved. A couple questions I usually get asked as regards to where does the expansion tank go on these guys here. I like to see it on the suction end of my primary pump, which you'll see right under there underneath that 12 equals PSI sign to the bottom left of the hydrocep. That's a great place for our expansion tank to go in that sort of system. So I'm just going to take a quick little break, and then we're going to come back and we're going to do our proven piping design systems. Okay, so we're going to be going through our last portion here, and this is going to be for proven piping design. Proven piping design, these are systems that we know work, we know how they operate. I'm going to tell you about the pros and the cons and exactly what is happening and why it works. Now, the first thing I want to talk about here is the placement of the very first few things that you see inside this system. We come out of the boiler, very first thing that you see on that red line is our high efficiency air separator. Right after that is our distribution pump. Attached to our high efficiency air separator is our expansion tank. This means that we are pumping away from the expansion tank. You always want to pump away from your expansion tank and not into your expansion tank, because if you pump into your expansion tank will absorb all the pressure that your circulator has created, usually creating in a low flow situation or even a negative pressure situation. This is more of an advanced technique, which we'll get into in a later training, but just know for your basic understanding, always pump away from our expansion tank. Okay, so this number one proven piping design is called a series loop, where essentially we're coming out of the boiler with a good hot temperature of like 180 degrees, hitting our circulator, and then we go into the first rad, and then continuing on in a series into each additional rad or heat emitter, whatever it is going to be. Now, one thing you will notice is that the color changing from dark red into pink and then into blue, meaning that as each rad is giving off its heat, the temperature of the loop is getting colder and colder. So that means that as a designer, we have to design each radiator to give off the right amount of heat at a cooler water temperature. Now there's all sorts of formulas that we can use to see how much temperature drop we're going to have from one rad to the next rad, but just know that this is going to be a symptom of using a series type design where you need to oversize your last emitter and usually undersize your first emitter because your heat's going to get lower and lower as you go forward. We don't do a whole lot in these anymore. These are usually for old cast iron systems. Still works well because we know it works and it flows, but there are some caveats with regards to the temperature drop through a system. This is your series loop. Old school technology. We've come a long way since then, but this does work when sized properly. Moving forward, we're going to have our diverter tees. These are also known as monoflow tees. What these are doing is they are forcing flow into an additional loop created off of your primary or main, usually into a radiator. Now these diverter tees are designed in a way that you see restriction on the hot side going in. As the water sees restriction going in here, it's going to force the water back up through the back side of the rad and then back down in through the tee and then on. This is called your monoflow or one directional tee, where that resistance creates your flow. And we still have the same problems happening in these guys here, where the temperature gets cooler and cooler as you go on. Also, it's getting harder and harder to find diverter tees. As far as I know, there's only 2 manufacturers of the diverter tees or monoflow tees out there right now, and that's B&G and Taco. There might be more, but just if you find yourself in a pinch, those are the first 2 companies that I would call myself to find these monoflow tees. This is also the very first system that starts to really kind of explore primary secondary, where a primary loop is the one from the system pump on, and then each individual rad portion coming off of it, that's going to be your secondaries. Not so much used anymore, older school technology, but it does work and it does flow. Moving down the line here, we're going to have what's called a direct return. This is where all of our rads for the first time are going to see the same water temperature being sent to each rad. Because what we have is we have our own individual supply line and our own individual return line, where we have all the hot sides coming off of the supply, and then it isn't until the last rad that we start to have the return coming back and catching all these returns on the way back. Now this makes a whole lot of sense, as now we don't need to oversize our rads anymore. Each rad is going to see the same temperature, but it becomes a little bit cumbersome with regards to the amount of piping that is going to be required. There are simpler ways to do it, and this one can get a little bit confusing in the installation side of things. Plus you need to increase and decrease. It's in your best interest, I should say, to increase your pipe sizing as your system returns and decrease it as your system is supplying out into those rads. So a little more math is required, or we can do it easier nowadays, but this style does work provided that it's installed and designed correctly. This one here is a much more common type application. This is referred to as a just a standard zone system, or what's called moose antlers, where you have your antler going your supply branch, and then you have your antler being your return branch. That blue is your return, the red is your supply. And each out of those supplies, you got a big pump sending it out into radiant zones or air handlers or radiators, whatever it is, where each of them sees the same temperature, and then each one comes back onto the return zone. Extremely popular style. Even nowadays, we see this all day, every day. But it has its, drawbacks as well, where, using this many pumps can be a little bit expensive, and you got to know your piping size correctly, where you're going to have that, 1.25 inch main and maybe 3/4 inch pipe sizing going into each individual zones. It does work very well. It's easy to zone, but there are more advanced ways to do it nowadays in the system. But this one here, you're almost guaranteed to see out in the field starting right now. Now you have the other way that you can do this, where it's the exact same situation where you're zoning, but now you're using zone valves for your distribution out to the system, where you have one central circulator creating all the flow for all the systems, and then your zone valves open as each individual zone calls. Now there's 2 different ways to do this. You have your constant speed circulator, where your circulator turns on, creates all the flow that you need as all those zone valves are open, sees no problem. But what happens is, not all the zones are going to be calling all the time at the same time. If you only have one of those zone valves calling, then the rest of them are going to be closed, which means you're going to have a whole lot of flow going through just that one zone, which means that you need to install what's called a differential pressure bypass, which is going to be collecting all that additional flow and sending that back into the return. If you don't have that, if you don't have the differential pressure bypass, all you have is the fixed speed circulator and zone valves. That will lead to what's called the banging zone valve situation, where the zone is going to be closing off against a very high pressure, such as the one zone valve calling and the rest are closed, and it's going to bang throughout the system. Now, if you've never heard a zone valve bang, it's incredible. It's going to sound like a shotgun is going off inside your house. Nobody wants that. So a differential pressure bypass valve is something that's going to be required when using a fixed speed circ. However, nobody uses fixed speed circs anymore. This is, this is 2023 now, and the world has adapted, and we all use variable speed pumps now for pretty much everything. And what these things do is they're going to be modulating the speed of the pump up and down based on a couple things, either pressure or temperature or a couple other things. But in this case here, we're going to put in a pressure regulated variable speed circulator. That is, all the valves are open. It sees very little pressure back against it. It knows that all of the zones are open. It's operating at full speed. As one zone closes and two zone closes, it sees more and more resistance against its flow because it's pushing against closed zone valves. No, it's going to slow down. It's going to create less flow to get in through the other zones that are still remaining open. That's the difference between a fixed speed circ and a differential pressure bypass and a variable speed circulator. You get much more efficiency, much more comfortable heat with the variable speed circulators than you will with a fixed speed. Again, you will see this out in the system all day, every day for the folks that do use zone valves. For the most part, most of the folks that I know prefer to zone with pumps. It is strictly a comfort thing. If you prefer zone valves, there is nothing wrong with zone valves. They work extremely well with a very long lifespan. You do you. I'm only here to help and assist how I possibly can. Moving down the line, we get into our real first primary secondary piping system, where your primary loop is the one coming off the boiler and then back into the boiler. All of our secondaries are going to be pulled off of your closely spaced tees. And again, your closely spaced tees, the rule for that is no more than 4 pipe diameters apart from each other, and that follows the rule of physics that what goes out must come in when we're talking about flow. So you will see as we kind of come out of the system, we have the same problems with this system as we had with our original series system, where each individual zone, if all of them are calling, you get colder and colder as you go on. Now, not all the time is that going to happen. Sometimes you're only going to have that one of these secondary circuits calling, or maybe it's only the last secondary circuit calling, where you need to design it in a way that it can see vast fluctuations in supply temperature and still not overheat the zone. This is usually done by controls or a digital mixing valve. Stuff like that can help get you around that, but for the most part, I don't do these systems anymore. There's too many caveats in the way that we can do better. Pardon me. And as we can do better, we should do better. And that kind of leads us into a bit more, a bit more advanced systems. But for those of you who just want to know, how do we even calculate what the temperature is going to be from one zone into the next of a closely spaced T system, this is the math that we use. So essentially, you use temperature. Actually, I'm not going to go through the math. If you want to sit here and study this slide, put me on pause, go crazy. Essentially, we use, the laws of averages to figure out what your temperature is going to be by the time you have flow and you're supplying your return mixed in with your supply temperature. It's essentially the average, but there's a bit more math to that. If you want to check it out, do it, but this is the actual proven physical math that shows you what your temperature drop is going to be through a set of closely spaced T's in a circuit. Here's another example of your primary secondary series piping. We also have the boiler on its own circuit off of your primary loop. This is what's going to be kind of known as your primary secondary injection, where the boiler is going to be injecting heat into that primary loop. It's again a tremendous amount of pipe. We don't do this a whole lot anymore unless we have to, and again, it requires pretty advanced controls to control all the temperatures going out into the system. But this is your primary secondary system, just with an injection of the boiler. And that leads us now into the bottom right-hand picture that I want you to kind of take note of here. This is your modern hydronic system that we have. Your primary loop from your boiler to your low-loss header and back, and then your system going out and zoned with either pumps or circulators, doesn't matter what. This is a true modern system where we have our high-efficiency air, dirt separator, magnetic separation, all of our pieces into ones, easy to zone. All of our zones sees the same temperature, designed for each individual zone to work. This is a proper modern hydronic system. This is kind of the ones that you want to see day to day, all day, every day. Extremely easy to service because we know that the boiler is always going to get the flow that it needs. System's easy to service because it's just a series of pumps. If the pumps are working, great, so is the systems. If the pumps stop working, now your system has stopped working. So really easy to diagnose and to troubleshoot. And that's essentially, you know, where you are now. Now, one last piece that I just want to show off, this is regard to what a manifold distribution type is like. Most folks use manifolds only for radiant inflow. Just so you know, there is a ton of applications you can use manifolds for, such as a home run system for radiators. It's an extremely fast and effective way to pipe in radiators inside of a home. Personally, I'm a huge fan of rads. Huge fan of rads. Radiant, take it or leave it. Radiators, yes please, fill your boots. Without getting onto a tangent, they are cost effective, easy to install, produce a ton of heat, can be extremely beautiful. I don't know if you folks have ever seen the Jaga rads, J-A-G-A. Go check that stuff out. And you can just, they're a lot more versatile and simple of a system where they don't require, you know, 10,000 feet of pipe inside of a system. Maybe now you're only talking about, you know, half a dozen rads to the exact same job. But my point being here, you can use manifolds to feed systems like this, where you're feeding different panel rads or different heat emitters. Don't be afraid to use your manifolds, you know, a little bit outside the box, other than just in-floor systems. So that's essentially, you know, what I have here for your hydronic training today. The last bit that was coming up there, that was with regards to domestic hot water and tankless sizing and stuff like that, which I am happy to continue to discuss at any time with any of you folks if you want to know a little bit more. But this is essentially your Hydronics 101. I hope you had a great time. I'm sure you have a ton of questions. I'm here in Equipco, Ontario, 905-612-1137. I'm happy to talk to any of you at any time for any reason. Questions, comments, concerns, design help, stuff like that. Whatever you need, you let me know, and we'll get you whatever answer we possibly can. Again, this is your basic, this is your intro. This is not to teach you everything. This is so you have good understanding of the questions and what's going to be coming down the pipeline. Can't stress enough, here to help. Contact us at any time. We got our number, got the website. This is all I do all day, every day. So thanks again for joining me, and I hope you have yourself a wonderful day.